Thanks a lot. Co-author on this talk, of course, is Uri Ten Brink. And the motivation for this study really is in some interesting and actually damaging meteorological tsunamis in the East Coast, namely the 2008 Booth Bay event and the 2013 event, which was observed in many locations along the East Coast as well as Bermuda. And to tie in really to a lot of the talks in this session, this event has been looked at as a landslide tsunami, and it's been going back and forth. A lot of the people at USGS Woods Hole and at NOAA have been trying to figure out the source of this particular tsunami. And I think the consensus is towards a Meteotsunami. So Uri and I were thinking, well, what's the likelihood of Meteotsunamis along the U.S. East Coast? So we're looking at this probabilistically. Meteotsunamis, of course, are tsunamis generated by a variety of atmospheric processes, squalls and atmospheric gravity waves, that kind of thing. And they do have a lot of similarities with landslide tsunamis for a number of different reasons. Typically, you see these in places where you don't see the large seismogenic tsunamis. They have waveform characteristics more similar to landslide tsunamis and seismogenic tsunamis. And one of the confusing things about the 2013 event is that the arrival times were coming from the slope shelf break, where you might expect to see a headscarp of a landslide tsunami. And in terms of the generation physics even, the Meteotsunamis are similar to landslide tsunamis. Basically, they're occurring through a coupling between some kind of phenomenon in the water column. So in landslides, if your landslide is moving at the phase speed of the long waves in the ocean, then you get maximum efficiency in the tsunami generation. So similarly, you have this, in Meteotsunamis, this Proudman resonance. You get maximum efficiency when the atmospheric disturbance is moving at the same phase speed as the ocean. So this would be for a Froude number of 1, and you get an amplification as the atmospheric disturbance moves across the continental shelf, given by basically the fetch of the disturbance, the speed u times the time of the disturbance as it propagates across. And this is multiplied with kind of the static amplitude change you expect from pressure change in the atmosphere. And that barometric effect, that delta eta star, is very small. So this Proudman resonance is important in order to get a significant tsunami generated from a meteorological phenomenon. There's other waves coming off these events. So these are the decoupled waves that are reflected at the shelf break and at the coastline that are very important. For Froude numbers greater than 1, you get a barotropic wake. If the disturbance is moving nearly parallel to the coastline and at the slower phase speeds of edge waves, you can get what's called Greenspan resonance. And then, of course, you get resonance in the harbors, but we're not going to be looking specifically at that. So probabilistically then, we can look at this similar how we deal with landslide and seismogenic tsunamis. So basically it's the same framework, and we're starting from the stationary Poisson assumption in which the probability that amplitude will be exceeded, wave amplitude will be exceeded at the coast is given by that survivor function exponential distribution where lambda is the rate parameter, or sometimes called the intensity parameter, and t is our exposure time. Usually in flood hazards we take that to be 1 year, so we're dealing with annualized probabilities. So this is our framework equation here. So here's our exceedance rate here, and we're summing overall types of sources. So for Meteotsunamis, you would sum overall squalls, atmospheric gravity waves. You could also be looking at all types of long wave hazards. So you'd be looking at seismogenic tsunamis, landslide tsunamis. That's how far you wanted to take that out. So for each source, you're going to have a long-term source rate. And then, as in one of the earlier talks, I think the first talk of the session, you integrate over your parameter space, which I just indicate for shorthand in terms of this parameter vector psi here. And then there's 2 terms here. This is the probability that amplitude will be exceeded for a given set of source parameters. And these source parameters will be essentially different for each source that you're dealing with. And then this is your size distribution of source parameters. And this is where it gets interesting in terms of Meteotsunamis. For seismogenic tsunamis, it's pretty easy because really the seismic moment or earthquake magnitude is really driving the tsunami hazard. So basically you hang all other kinematic parameters off the seismic moment distribution, so your moment area scaling relationship, for example. On the other hand, if you look at storm surge forecasting, where meteotsunamis really kind of fall closer to, you have a number of parameters that are more equal in terms of driving the hazard. So this becomes a more complex joint distribution of source parameters that I'll discuss in a little bit here and how we deal with that. Basically, we use a lot of tools available from storm surge forecasting. This shorthand compact version of the equation is actually implemented using Monte Carlo sampling of the parameter space and, most importantly, numerical modeling of the phenomenon. So here's our hydrodynamic model. Let's see if I can get this going, yes. Of the 2013 event. Here's our coupled wave propagating with atmospheric disturbance propagating across the continental shelf. And you can see the decoupled waves quickly propagate out into the deep ocean. But most importantly, you get this prominent reflection from the shelf edge break. This is Long Island, of course, and it's going to reflect off Long Island, so, and Delaware Bay here. You're going to get a lot of wave activity in this New York Bight region from this particular event. And you can see it gets complicated quite quickly here. This is a linear long wave model with 1 arc minute grid spacing and a half-second time spacing. So here's our comparison of our model results, and here we're just looking at the maximum per event amplitude because that's what we're going to be calculating in terms of a probabilistic hazard curve. Here's our model prediction in terms of the blue line, and the red lines are the maximum amplitudes observed at the tide gauge stations for the 2013 event. And you can see below about Atlantic City, the amplitudes drop off pretty quickly here. And the amplitudes are quite higher in this New York Bight region, but still quite variable too, at least from our model. I should also mention some other detailed papers that have recently come out on this particular event in terms of deterministic studies. So here's our model domain. We're going to try to see how this works in reality. We're going to look at the Northeast Atlantic region. This shows our hydrodynamic model domain and the bathymetry that we use. It also shows our output and input. We're going to be outputting hazard curves at the tide gauge stations listed here with the black circles. And our input data for all the parameters involved come from the Automated Surface Observing System, ASOS stations, which are these weather stations shown with the red dots here. So we're getting a lot of these parameters, especially the pressure parameters from the ASOS stations, as well as from Doppler radar that's been archived. So from the year 2000 to 2013, we detected 116 squall events. I should mention we're just looking at squall events for this little case study. The reason we don't go before 2000 is that the ASOS stations really started the high sampling periods of 1 to 5 minutes at the year 2000, and before that it was a hourly sampling rate. So getting back to this joint distribution of parameters, I fully expected from looking at some storm surge studies that there'd be some correlation among the different parameters and would have to deal with a quite complex joint distribution. But for whatever reason, and perhaps we're just looking at a limited period of time here, there doesn't seem to be much correlations between various combinations of these parameters and the scatter plots. And this allows for a simplification of that joint distribution where we can just express it as the product of the marginal distribution for each parameter. So here's our pressure change, the speed of the atmospheric disturbance, the period of the disturbance, which we convert to the width, and the length of the disturbance. And then again, this is our modeling term here. So we fit various probability distributions to each of these parameters shown here. We tested a number of different distributions, and it turns out either the normal or log normal distributions fit the best. Here's our fit to the cumulative probability distributions. The red lines are the analytic best fit distributions, and the blue is the empirical distribution from the ASOS and Doppler radar data. So for most of the parameters, we're getting actually a pretty good fit. So here's our end result. This is a tsunami hazard curve for meteotsunamis at Atlantic City, New Jersey. So what we do is we build a synthetic catalog, and we try to make that synthetic catalog reflect the input data. So We have 116 events in our synthetic catalog. And it only spans that 13-year time period, so we're only going down to a mean return time of about a little less than 10 years. So we sample that, so each synthetic catalog results in a hazard curve shown by the thin blue lines. We run that 20 synthetic catalogs for a total of 2,320 events. Each one of those, we run a hydrodynamic model. So we get this suite of hazard curves, and the mean hazard curve is shown by the solid blue line. You can see it's pretty flat, power law-like here, and then it bends over at certain rates here. I should explain, unlike a lot of tsunami hazard curves that you see, most of them assume that the exceedance rate here, that lambda parameter, is identical to the annual exceedance probability, that p equals 1 minus e to the lambda minus lambda t. But since these events are very frequent, that, of course, doesn't hold for the more frequent events. So I plot the annual exceedance probability on the right-hand side as well. And we do have an observation point we can compare to our calculated hazard curves. There was, from tide gauge, filtered tide gauge stations at Atlantic City, there's 12 Meteotsunami-like events from late 2007 and 2011. So I think we're doing a pretty good job. We might be over-predicting the hazard based on our parameterization of the problem and some of the simplifying assumptions that we use. Now, to extrapolate this out a little bit, we use a fitting function that we've used before with a number of other natural hazards in this paper with Tom Parsons. It's the taper Pareto distribution. In the first talk of this session, they mentioned the generalized Pareto distribution, which we use as well here. So we can now extend this out to mean return times of 100 and even 1,000 years shown here. We are seeing some difference in the physics in these hazard curves. So we're seeing, especially at high rates, we're seeing flatter hazard curves indicating a higher hazard in the Montauk, Atlantic City region. Basically, they're in this New York Bight region where you get waves from different sources, reflected waves, decoupled waves from different sources, and you have a fairly wide continental shelf in the direction of these storm tracks. Whereas farther south in Chesapeake, you have a much narrower shelf and less sources of the Meteotsunami waves. So future work, of course, if you wanted a comprehensive analysis of Meteotsunamis, you'd have to, of course, include all sources of Meteotsunamis, which gets to be quite difficult, especially for some of them, because you need, rather than a simple parameterization, you have to really run an atmospheric model for some of them. There are some non-stationary probabilities we should probably look at in terms of seasonal effects and long-term sea level rise. And there's a bunch of tools from the storm surge forecasting community that could be used, including storm track modeling, as well as ways to optimally sample the joint probability distribution, just because our computational load is so high for any kind of probabilistic tsunami hazard modeling. And I always have to leave out the possibility of these parameter distributions being heavier tailed than normal or log normal. We're just looking at a short amount of time, and I know from hurricane studies, like the central pressure is often a higher tailed or heavier tailed distribution than what we've used here. So in conclusions, I hope at least in terms of the theme of the session, to share with you that at least Meteotsunamis do share a lot of the same characteristics as landslide tsunamis, and they can be confused with each other. We can use the same type of probabilistic framework as we use for geologically induced tsunamis. It's that joint probability distribution that we have to be a little careful with, and we can use a lot of the tools from storm surge forecasting to really deal with that. Overall, the hazard of Meteotsunamis is much more frequent, but it's much less severe than geologic-induced tsunamis. The caveat is we've only looked at squall sources and a short amount of data, really, to build our parameter distributions. And as always, data, meteorological data, and these atmospheric models, I think, are key to advancing probabilistic analysis in the future. So for future details, I refer you to in this paper down here in a special volume on Meteotsunamis and natural hazards. Great. Thank you very much. Yeah. Yeah. Yeah, that's a very good point, and we didn't look at harbor resonance, and so the point was that these are very short wavelength phenomenon and can really resonate in a lot of these harbors. So the 5 meters, yeah, this is a long extrapolation to get to there, but yeah, I mean that's a pretty. No, you're right. At the 1,000-year mean return time, that's what it is from our estimate. Sure, sure, yeah, yeah.
You showed very convincingly that the various source properties were more or less uncorrelated. That's pretty clear. But to capture the source function, you don't necessarily need pressure, wavelength, and speed. Did you try using a sort of more parsimonious source function? And if you did it make any difference?
Well, again, we used independent parameters. Actually, what we used as a source function, kind of a shape function, is one we've used from landslide tsunamis. Part of the trade-off is, and I don't know if that goes to your question, is that in terms of the hydrodynamic modeling, you need a pretty smooth source function in order to prevent a lot of the instabilities that arise in some of the finite difference method. So we didn't look, we took a lot of the shape of the source function from previous studies of Prudman resonance from Vilibich, I believe, but we haven't looked exactly the source function in terms of, especially in terms of atmospheric modeling, what that might look like. That would be definitely a useful next step to do, yeah.